Okay, today we're moving on to chapter 10. So again, this wraps up convection. So we had chapter 6 was sort of an introduction to the basic principles of convection. Chapter 7 was external convection. Chapter 8 was internal convection. I consider chapters 7 and 8 to be sort of the most important. Chapter 9, we did natural or free convection. And then chapter 10, we're doing boiling and condensation. So chapters 9 and 10 get into some nitty-gritty stuff that you probably won't remember long-term, but still some of the concepts here are important. Okay, so if you didn't know this already, boiling is associated with changing a liquid into a vapor. So it typically happens because there is a solid and liquid interface, and over that interface, convection is happening. So you heat up a solid surface, that solid surface interacts with the liquid that is adjacent to it, and it starts, as the heat goes into the liquid, at some point that liquid will want to go through a phase transformation because it crosses over its boiling point. So when convection happens, as you start getting bubbling, that causes agitation in the fluid. So what did we learn about when we talked about laminar versus turbulent flows and convection? Which one, between laminar and turbulent, which one tended to have the higher heat transfer rates? Turbulent, okay, why turbulent?
Eddies create mixing.
Okay, great. So Kyle's saying that eddies create mixing. So as that turbulent flow starts going, it's agitating the fluid. That mixing is a really good thing for heat transfer if you do want heat transfer. So that agitation and that bubbling and boiling tends to make heat transfer coefficients pretty high when you're talking about boiling. They're also pretty high when you're talking about condensation. Sorry about that. Okay, so we're going to be dealing with a special form of Newton's law of cooling, which looks just like the Newton's law of cooling that you should be very, very used to now. However, our delta T is something termed the excess temperature, and that excess temperature specifically means the difference in temperature between our surface temperature and the saturation temperature of the liquid. So putting that into Newton's law of cooling, we just see that flux is proportional to H times surface temperature minus the saturation temperature, which goes into this delta T sub E. So just remember that delta T sub E means at the excess temperature. It's the temperature at which your surface exceeds the saturation temperature of the liquid. Okay, so these are some numbers that I just pulled. I don't know if you guys have ever used the website Engineering Toolbox. It's usually, if you Google like heat capacity of a material or thermal conductivity material, this is usually one of the top hits that comes up. So this, I just queried this quickly to show you typical convection heat transfer coefficients for common fluids. So let's look at the top ones first. We talked about free convection last week. So when it's air or gases, you would expect to see free convection coefficients on the order of 0.5 up to 1,000 watts per meter squared Kelvin. They're a little bit higher for water and liquids. Liquids are going to have a higher thermal conductivity. The molecules are all closer together, so naturally they're going to transport heat a little bit better than vapors and gases. Then when we go to forced convection, you'll notice this increase on the bottom limit. So if it's air, gases, and dry vapors, in free, from 0.5 we go up to 10. So forced convection helps things. The water one, we see an increase in the upper limit here from 3,000 to 10,000. So generally, with forced convection, you're going to see higher heat transfer coefficients than you do with free convection. So now, when we go to boiling and condensing, I want you to take a close look at the magnitude of these numbers here. So for boiling water, now our lower limit is 3,000 watts per meter squared Kelvin up to 100,000. When there is condensing water vapor, we're at 5,000 to 100,000. So this is one of the key takeaways of boiling and condensation, is when you have these things happening, that tends to drive your convective heat transfer coefficients really, really high. In the case of boiling, that is largely due to this extra mixing and agitation and bubbling and circulation that happens when the fluid is boiling. So that tends to be really good for heat transfer. So again, boiling and condensation, a key takeaway is you get really, really high rates of heat transfer. So let's suppose, I'm going a little bit off script here, let's suppose we had some kind of heat exchanger where we had a fluid here and maybe a solid interface. And then here, for whatever reason, we have a boiling fluid. So this might be some kind of hot heat transfer fluid, like some kind of hot thermal oil or a molten salt, and it's used to boil water to make steam. So if we're looking at this from an overall heat transfer coefficient point of view, so we would have our total thermal resistance would be equal to, and let's do this for the 4-unit area. I didn't do that on the slide, so I just totally lost it. Okay. Okay, so here we have a boiling fluid. Here we have just a hot fluid that's, and then we've got a solid. Okay, so the hot fluid, let's say it's flowing this way so that we have some kind of forced convection. So you guys would know how to find out a convective heat transfer coefficient for that hot fluid, right? How would you generally do that? So we'd use a Nusselt number correlation and we'd back solve for H. Great. But that H alone wouldn't express the total rate of heat transfer all the way through. So if we wanted to take fluid from this hot fluid through that solid metal wall into our boiling fluid, there are going to be 3 thermal resistances. So our total thermal resistance per 4-unit area would be something like 1 over H for this forced convection, plus L over K, plus 1 over H for the fluid that is boiling. So what would it tell us if we made the assumption that the heat transfer coefficient on the boiling side was really, really high? How could we reduce that equation? Okay, we could just make the last term 0. That's great. We could just neglect this last thermal resistance. So if this H boiling is really, really high, that'll make this term trend towards 0. And so we could look at our total thermal resistance as just the forced side plus the conduction through the wall. So we could just neglect it. We'd be neglecting that thermal resistance. So if you think about a fluid that's boiling and it's doing all kinds of circulation, it's taking heat from that solid surface and it's just moving it away very, very quickly. So the thermal resistance tends to be very, very low. So we could just neglect that thermal resistance and just account for those other 2 terms. So you could also do something like assume that the wall is really thin. We'll be doing this on, oh, actually, I guess we're not doing this because I just give you U. Often you can make this thin-walled assumption when you're talking about heat exchangers. So if we made an assumption that we don't really care about the thermal resistance of that solid material, what does that allow us to do for our total thermal resistance equation? Okay, yeah, that would let us assume that L is small. So we could neglect that thermal resistance as well. So when you get boiling, one of the assumptions you can make is that there's no thermal resistance because that boiling just takes the heat and immediately sweeps it away. So the thermal resistance tends to go to 0. In certain cases, if you found that this H was significantly higher than this H, then this H would become the limiting factor, and that would basically be the main component of our overall heat transfer coefficient. Okay, so boiling is certainly a very important process for chemical engineers, for just anybody. We rely on this process of boiling in so many different ways. So one of those is power generation. So this is what's called a water tube boiler. So what happens in a water tube boiler is you have a large combustion chamber, in that large combustion chamber, you are burning a bunch of coal or a bunch of gas, and then you have these tubes come down. This is called a downcomer, and this is called a riser, and that water is going to circulate through the boiler. So basically it's actually a water vapor mixture. This water vapor mixture will come down, pass through the firebox of the combustion chamber, where it's going to have heat added to it. Then it's going to rise back up and sit in this steam drum. So through these tubes, we have a boiling process. Convection here doesn't happen just by boiling. This is also forced convection because we have an active flow going through those tubes. So we could certainly use some of the boiling heat transfer correlations that we're going to cover today in these tubes to figure out what our H is. On the other side, we have a process that's going to be largely driven by radiation. So we're going to have radiant heat because the temperatures get so hot that radiation tends to dominate. That radiant heat is going to hit the outside surface of these tubes. It's going to have to go through the tube wall and then into the tube itself. Any questions here? Okay. Then on the right, we have the one on the left is kind of cartoony. The one on the right is a little bit more technical. So you have this fluid that circulates between the downcomer. It goes from the steam drum down into this bottom drum. This is also called a mud drum, and that's just sort of to give the system a pool of water so that it can circulate back up. It's also a way to collect kind of nasty stuff, and you can do what's called blow down. You can start sucking some of your nasty fluid out of there and dump it down the drain or whatever you're going to do. So typically, to increase the rate of heat transfer, if you step inside one of these, what you'd actually see, you'd see a big room, and then the walls would be almost entirely covered by tubes. So taking advantage of all that surface area to maximize exposure to the flame and therefore the rates of heat transfer. Okay, so boiling actually gets kind of interesting. It's divided into a bunch of different categories, and this one category called pool boiling actually has several different phases, which are kind of interesting to think through. So pool boiling has a lot of different phases. It starts with natural convection, then there's bubble-induced mixing. You get into nucleate boiling, then transition boiling, and then film boiling, and we'll actually cover those in more detail in a couple of slides. There's also forced convection boiling, which is when you have when you have boiling combined with forced convection, just like we saw in the boiler. You'd have those tubes passing through your firebox, and as the water goes through those tubes, heat transfer happens because of the flow of the fluid, and also because of the bubbling and mixing and boiling that happens inside the tubes. There are also some others, saturated boiling and subcooled boiling, which are kind of interesting. We won't focus on those, but that's where your surface may be at a slightly different temperature than your bulk fluid. And so what happens at the surface, you may actually be above saturation temperature at the surface, but then saturation temperature in the bulk. And in subcooled boiling, you may be subcooled in the bulk and then at or above saturation temperature right at the interface. Okay, so this is something called the pool boiling curve. And I'm going to show this. I think my next slide is this, but bigger. Yeah, okay. So this is what happens in pool boiling. So notice we have our delta T excess. My apologies for the resolution. This is a lot better picture than the one included in your textbook. So on the bottom we have that delta T sub E, that excess temperature, which is our surface temperature minus the saturation temperature of the fluid. Then here, the nomenclature is different than our book. This is a flux term. So that's the flux that goes from our surface actually into the bulk fluid. So this plot shows as we increase our surface temperature, how much flux are we adding? So this is much, much different than what we've typically seen with convection, and we'll cover that in a minute. Okay, so in the first phase, when we get our surface temperature just slightly higher than the bulk fluid temperature, we would have something called natural convection boiling. So in natural convection boiling, we get the surface heats up. It would, in all likelihood, is going to be hotter than the bulk fluid temperature. Well, it definitely is going to be hotter than the bulk fluid temperature. So as that happens, we're going to get a little bit of conduction happening from that surface into the bottom layer of fluid. So what's going to happen when that bottom layer of fluid gets warmer than the rest of the fluid? Is that a stable or an unstable condition? Say that again? Unstable. Okay. So that's an unstable condition. Great. So we have this hotter fluid, just like we covered in natural convection. So that hotter fluid is going to want to rise. As it heats up, it's going to expand slightly, so it's going to be less dense than the colder fluid on top of it, which is going to create some natural current and natural circulation. So that's called natural convection boiling. As we keep increasing our excess temperature, so we keep on adding heat to our heating element, you start to get bubbles that actually form. So as those bubbles form, they're going to start to rise to the top. As they start to rise to the top, they're going to encounter the cooler fluid, and they're going to condense back down and come back down. So that is what happens in the early stages of nucleate boiling, is the bubbles, they start to rise up, but then they can't sustain themselves and they collapse. But that causes a little bit more circulation, so you notice that our heat flux is gradually increasing the higher and higher we make our surface temperature. So at some point, we get that the bubbles actually rise to the surface. So that's sort of the second half of this nucleate boiling stage. So when the bubbles rise to the surface, now you've got this much more vigorous action happening. You've got this really well circulating fluid, and your heat transfer rates are maximized at that point. So that's where your maximum heat flux occurs. So then there's something really interesting that happens. As you continue to add heat, you've got this really vigorously boiling steam and water mixture. As you keep adding more and more temperature to your bottom surface, your heat transfer rate actually starts going down. Anyone have a sense as to why that would start going down? Okay. Okay, Justin, right? Joseph, man, I do that every time. Okay, Joseph is saying you start to get a layer of, someone said air, this would actually be steam. So you start to get a layer of steam building up here on the bottom. And so what that steam does is actually introduces a new thermal resistance coming from our surface into the bulk. So now we know that heat transfer is going to happen a lot better in a liquid. Well, now you get this, you start getting these pockets of vapor building up here. So that creates a new resistance to heat transfer. So you have this extra resistance to heat transfer now, even though you're increasing your driving force. So even if your surface temperature is getting up to something like 180 degrees C, you would still see your heat transfer rates going down. So then what happens, and that is called the Leidenfrost effect, as Joseph pointed out. So that keeps happening until you get to something called the Leidenfrost point. So that's sort of this point of minimum heat addition. Then we see heat transfer rates start going up again, which again is a little bit weird. Anyone sense why they would start going back up again? Yeah, James? Okay, so James is saying, yeah, we keep on heating up our surface. We keep adding more and more temperature. So naturally, even with this little vapor film or this blanket of stuff, we've increased our temperature so much that heat transfer rates have to start going back up again. We've already got that vapor film there. So naturally, if we keep on adding more heat and increasing our surface temperature, naturally that's going to go back up at some point. And what happens physically is actually radiation starts taking over here. So now, if you remember, radiation, unlike convection, has the driving force is temperature of the surface to the fourth minus temperature of, in this case, the liquid to the fourth power. So we start to get heat radiating across that vapor film. And that driving force for heat transfer, as you keep on adding more and more temperature to your surface, eventually that T to the fourth takes over and you start adding more and more heat. And that's, we get into something called film boiling. And film boiling basically means you get this vapor film or this vapor blanket on immediately adjacent to your surface. Any questions there? Okay, so that is all the different phases of pool boiling. Okay, so I want an interactive problem. If you downloaded the slides, I changed the wording of this slightly, so go with what's on the screen rather than what's on your downloaded slides. So because the mode, we're still talking about convection. I'll give you a hint that Newton's law of cooling is still going to apply here. Actually, we covered that a few slides ago. So Newton's law of cooling for boiling still represents a linear process. Is that true or false? All right, and I'll show the answers once we get 20 students. Maybe 25. Okay, so most of you said false, which is the correct answer. So even though that Q simple form of Newton's law of cooling is still the same, Q equals HA delta T, this is no longer a linear process. So someone want to explain, someone who answered false want to explain why? Yeah. Okay, so John? No. Zach, sorry. Zach says our H is now varying, which is totally correct. So now our H is no longer going to be a constant. So it's important to remember that while we have this pretty equation that looks really simple, H is now a strong function of our delta T. So H is equal to a function of delta T, and specifically it's the excess temperature. So now our H is going to change dramatically based on what our excess temperature is, just like in that curve that we showed. So while that scale, shoot, I did not mean to do that. So while the scale here is logarithmic, we still see that our Q, it doesn't have this nice continuously increasing curve. It's going through this transition. So all that's ultimately going to be built into our H. Okay, so let's think through this whole process a little bit more. So if you remember, we got to this maximum critical flux when we have this really nice healthy boiling. Our bubbles are forming at the surface, and then they're rising all the way to the top. They're not collapsing anymore. So we get this nice vigorous boiling, and that maximizes our heat flux. If we kept on adding heat to our heating element, and we started going down this line where we start forming that vapor film, do you think that process is going to be fast or slow? So I guess the question officially asks, if you're trying to heat a liquid from subcooled to film boiling, you should expect the transition part of the process to be relatively short in duration. So is that true or false? If you have no idea, just take a guess. Yep. Okay, so most of us are saying false. It's a tricky question for sure, and there's probably not a super clear answer. There is a point here that I want to illustrate, though, and that is, so we keep on adding, did not mean to do that. So we keep on adding heat. If we wanted to increase our surface temperature, let's just imagine, in my head, I have a pot of water boiling on a stove because it's the simplest thing I can think of. So we keep on trying to increase our surface temperature, which means we're cranking up the power that we're delivering to our heating element. So we keep on cranking that up and cranking that up, but at some point, the amount of energy that's actually getting into our fluid starts going down because of that film effect, that thermal resistance caused by the film. So if we continue to add heat to our heating element, but that heat isn't actually getting into our fluid, where is that heat going? Okay, into the film. It's going into our system. It's going into actually heating up our element. So we're going to have this sudden extra thermal resistance. It's basically a layer of insulation, and we keep adding heat, so our heating element is going to heat up really, really quickly because there's nowhere else for that heat to go, right? At least it's not getting into the fluid as fast as it was before. So that's a pretty unstable process. So we would expect to get through this little transition fairly quickly because we're going to keep adding heat, and that heat is going to go directly into our heating element. Okay, and we'll revisit that here in just a minute. So putting this out in slide form, so in nucleate boiling, first we start, after the natural convection stage at least, we start getting nucleate boiling. So first you have isolated vapor bubbles. So liquid motion is strongly influenced by nucleation of bubbles at the surface. So those bubbles will start, if you've ever seen a pot of water boiling, you'll notice all those tiny little bubbles that start to form. So that's the early stages of nucleate boiling. Then you'll see that H and heat flux sharply increase with our delta T. And this goes back to that point that unlike in everything we've covered so far, our H is actually going to be a function of our delta T. So our H itself will increase. So heat transfer is principally due to contact of liquid with the surface and not due to vaporization. Okay, then when you start getting into jets and columns, so you get more nucleation sites. The liquid surface contact starts to be a little bit impaired because now you're getting all these bubbles forming. So, but Q, it continues to increase with delta T, but H begins to decrease. That's when our curve stops being so sharp and it starts to get toward that critical point. So once we get to the critical point, that's the maximum attainable heat flux you can get with nucleate boiling. Beyond that, you're getting into the transition going to film boiling. And as I mentioned, if you do this, if you keep on adding more and more heat to your burner, you risk burning out your heating element or your flame, or you risk actually starting to melt the metal that you're using as your surface. So that is called potential burnout, and that's just because you keep on adding heat, but you run into this thermal resistance. So it's a very unstable process. And finally, you get into film boiling, and that lead-in frost point, which is the point at which radiation heat transfer starts dominating as heat starts to cross that vapor film by radiation. Okay. So some interesting theory there. Now let's get into the correlations that we've all grown so fond of. So to calculate the amount of heat going in, you can use this Rosenau correlation. So this just tells us that our flux is equal to the viscosity of the liquid. Notice these subscripts, that L stands for liquid, V stands for vapor, and just to make things even more confusing, HFG is it's the heat of vaporization going from a fluid to a gas. So that's should be, to be consistent, that could be HLV alternatively. So that's dependent on gravity, on the density of our liquid and our vapor, also the surface tension of the liquid. So it is dependent on our excess temperature as well as heat capacities, and then another parameter that you have to look up in table 10.1 of the book. So again, if you can't tell, this is a really nonlinear process, and here we're calculating Q. If you use this correlation, you're sort of ignoring Newton's law of cooling and just calculating it directly by this correlation. So you can see by that delta T sub E to the third power that this is going to be a highly nonlinear correlation, a highly nonlinear relationship. You can also calculate the critical heat flux using this Zuber correlation, which is a little bit simpler, but it's right there. Okay, so when you get film boiling, now we start getting into more Nusselt number correlations. So if you remember in film boiling, radiation is a big part of that, so we have to factor in radiation in that case. So if we wanted to calculate our average H, this rule of thumb is useful. So our average H raised to the 4/3 power is going to be approximately equal to our convective heat transfer coefficient average that we would calculate with this Nusselt number here, then our radiation heat transfer coefficient, which we covered, I think, way back in chapter 1, multiplied by H. So this is a dependent correlation. You'd have to solve this iteratively. To get the convective heat transfer correlation for film boiling, you would use this correlation to solve for it. Okay, so we're going to move into condensation now. So we went through some interesting theory on boiling, and we got to a correlation where we're calculating Nusselt number. We're starting to get to really high temperatures here and really complex effects where you have the boiling itself happening, and now we're even getting into radiation with all of its beautiful nonlinearities. At the end of the day, the Nusselt number correlation will be really important, but really a very key thing to remember as engineers is when you have boiling, it's usually a pretty good chance to neglect thermal resistance. So we may just assume that our H is really, really high relative to the other thermal resistances that we're caring about, and so we could neglect that thermal resistance on the boiling side and just figure out what's happening in the rest of our system. So that would be basically making the assumption that the boiling fluid is just mixing really well, so it's carrying away heat from the surface extremely quickly. Okay, now for real, we're going to get into condensation. Okay, so prior to my life as a professor, I worked for ExxonMobil, a big oil company. I did a lot with our boilers and with our steam systems. So this is the complex where I worked. This is actually bigger than the hometown that I grew up in, and it's just this huge, huge facility where you just have pipes all over the place. I would frequently have to park under a big rack of pipes. They're just all over the place. There's just equipment everywhere. A lot of those pipes are carrying hot fluids, different components of crude oil or refined products. We would actually generate steam in boilers at a central location and then send that steam out to this whole complex. So condensation actually kept me up late at night because I had the unfortunate task of running a control system that had to respond to rainstorms. So when we had rainstorms, who here has ever spent a couple of days in Houston or several weeks in Houston area? Who here has experienced a rainstorm like on the Gulf Coast? So we had a bunch of rain over the weekend. How does that rain compare to like a Gulf Coast rainstorm?
It's a lot colder.
Colder. In terms of actual like rainfall rate, it's like you could step outside and just be soaked immediately. We had a gauge that would actually collect rainfall data, and I created a little calculation to estimate how fast rainfall was happening, and there were times when I recorded 6 inches per hour of rainfall. So here in Salt Lake, I believe we set records back in like March, April, and May for we had a lot of rain, if you remember. I think we had 3 inches total in each of those months. So 6 inches per hour. So one thing that would happen is this rainfall would hit our pipes. We tried to insulate them very well, but when you have miles and miles and just thousands of square meters of pipe surface area, rainfall becomes a big enemy. So that rainfall would hit the outside of our pipes. So on the outside of the pipe, if that rain hits a metal surface that's super hot, what's going to happen? So it's going to evaporate, which is going to suck heat away. Then on the inside of the pipe, if those were steam pipes, all that heat that you're sucking away from the surface is removing heat from inside the pipe ultimately. So you get condensation happening on the pipes. So if those pipes were near their saturation temperature and pressure and you suddenly remove heat, what's going to happen to that steam inside? So it's going to start to condense and fairly quickly. And the fact that condensation leads to higher rates of heat transfer was really a bad thing. So in these big rainstorms, we would actually see our steam pressure go down really, really quickly, which had the potential to shut down particular units that I was responsible to maintain. So Anyway, condensation is a really important process. You see it in a lot of different places. So this happens, you can have so if you have a pipe that's carrying vapor and it starts to condense, that of course is going to first happen on the surfaces. And then as that happens on the surface, you're going to get droplets forming. Those droplets will ultimately fall to the bottom. So condensation is an important thing to understand and to get your head around. Even absent some emergency situation like I just described, it's pretty important to remove liquid from a pipe that should be carrying a vapor. So if you get sudden slugs of water, that's something called a water hammer. So that can cause mechanical corrosion. If they're little droplets, they can be just gradually wearing away at the surface of your pipe. They can cause noise, they can cause vibration, they can actually cause pipe collapse. So in chemical systems, they make a pretty active effort to remove any condensation that builds up with something called a knockout drum or a knockout pot. So there will just be a place in the line where there's a little vessel, and that vessel will allow fluid to condense, and then every once in a while your control system or a person will go and open up a valve to drain all that out. So they actively try to knock all those vapors out. And actually, if you have a feed coming in, there's going to be some separators here, maybe even cyclones, and they'll hit some kind of mesh here, and that'll allow the vapor to pass through, but that'll encourage any liquid to form droplets and then drop out of this thing. Okay, so this is an example of a steam distribution system. This is a very, very simplified example. So you might actually have several different levels of pressure in your steam line. So you might have superheated steam at high temperature and high pressure. That might be like at up to 1500 psi. You could go down in various phases. We typically had problems with our 150 psi line because that was the closest to, it was the coolest and the closest to condensing. Okay, so you also encounter condensers just in regular chemical processing. So have you guys covered distillation before? Does anyone know what distillation is? You'll know very well next semester, I think. Okay, so in distillation, you have some kind of feed that has a bunch of different components, a bunch of different chemical components. Those chemical components you want to separate them for whatever reason. So in oil refining, you bring in crude oil, which is actually composed of dozens or hundreds or even thousands of different chemical compounds. And so you generally want to separate that into things that would be good for like gasoline, or things that would be good for diesel fuel, or things that would be good for like engine oil. And the very bottom stuff is going to be something that eventually will become road tar or rubber or something. Actually, rubber still has to go through some processing steps. So you separate these different components because they have different boiling points. So through the top, you're going to get a vapor containing your light component, or your light key. At some point, you want to get that back into a liquid phase so you can transport it easier. So that'll have to go through a condenser. So a condenser is something that actively condenses a vapor back down into a liquid by some kind of heat exchange with a colder fluid. You will also see condensers in power cycles. So we talked about, this is an extremely simplified boiler system, but you basically make steam and use that steam to drive a turbine. Then you want to get that steam back into a liquid phase so you can pump it back up to high pressures and use it again. So you'll have a condenser doing that. So in this case, these are typically a cooling water cooled condenser. So you'd bring in the steam, you'd have a heat exchange with cooling water, which is coming from a cooling tower. And then that's going to condense it, and it's going to go back into a pump, and you can start that process again. Each of you most likely has a condenser in your home or apartment. That's the thing that you see outside on the ground that is condensing that refrigerant back down. So if you're doing air conditioning, you bring in this really cool refrigerant. You run it through your evaporator. So the evaporator is actually where you are sucking off heat from this. You're evaporating the refrigerant but you are cooling down the air that's coming into your home or apartment. So then that refrigerant is cooled, it evaporates, then you compress it back down. After you've compressed it, you need to remove heat and reject that heat back out to ambient. So the condenser is condensing your refrigerant back down before you can run it through an expansion valve and start the cycle again. So this is what your compressor / condenser looks like. So all around the outside of this, if you looked carefully through those little slits, you're going to see little tubes that are circled about with little fins, little aluminum fins, and there's just a ton of surface area that happens there. But the whole objective of the condenser part of this is to condense your refrigerant back down. So back into more of the theory of condensation. So you can have film condensation, which is when your entire surface is covered in a liquid. There has been a substantial enough liquid that your entire surface is wetted, so it's all in contact with the film. You can also have dropwise condensation, which would be the early stages of film condensation, or you could just have dropwise condensation at steady state. So you may have some kind of surface that you don't want film condensation to occur for whatever reason. So dropwise condensation is when you do not cover the entire surface with your condensing liquid. The same concept of a boundary layer will happen as that film starts to coat your surface. Then we'll have flow starting to happen. You'll form a boundary layer, and you'll have to figure out what's happening between the surface and the vapor here in the bulk. So as we've covered with laminar flows, you can actually solve a lot of this mathematically. In this case, we're making the assumption that we don't care, we're neglecting any advection in the film, so we're assuming that our temperature is the same from the surface out to here. So that allows us just to solve the momentum equation. And going through the solution, you can actually calculate the film thickness. So the film thickness looks like that. Again, it's expressed in terms of delta. I'm trying to get through these in the next 5 minutes. So you can calculate the flow rate per unit width. That's that gamma term. So that's the mass flow rate, where B is the width of the wall that you're considering. And finally, we get back to our old friend, the Nusselt number. So we can calculate an average Nusselt number if we have all of these different parameters of our film. So we need to take into account things that have the subscript L, which would be properties of the liquid, and things that have a V, which would be properties of the vapor. So going through these steps, we can plug and chug, and we can end up with our average heat transfer coefficient. And we would basically use an equation that looks like this. So at the end of the day, despite all the complex things that are happening, we're going to find ourselves using a correlation to calculate our average heat transfer coefficient. So just like in forced convection and free convection and in boiling, in condensation, you can get to a point where there are correlations that exist to calculate your heat transfer coefficient. So this is something, if you're solving a problem, you'd certainly want to understand if there's boiling or condensation happening, so you could use the appropriate equation. If you were to miss a detail like that, you're going to end up getting heat transfer coefficients that are way, way too small. Because if you use the proper equation, you'll find that boiling and condensation tend to drastically elevate the convective heat transfer coefficient. Okay, I think I'm just going to stop there. So you do need to consider whether the flow is laminar or turbulent. There's a different correlation if you have horizontal flow or vapor flow in a horizontal tube. If you have condensation happening, here's your Nusselt number correlation, where you'd actually factor in the quality of your fluid, as in how much of it is a vapor versus how much of it is a liquid. And that's it. So this chapter, as in chapter 9, gets pretty hairy. I tend to find a really hard time asking exam questions based on this stuff. There may be a correlation that shows up. Who knows? But just a reminder, on Wednesday, come prepared to do this flipped classroom where we're going to make this transition from convective heat transfer into heat exchanger. So this flipped problem is going to be a nice segue into how do you apply the principles of convection to simulate a heat exchanger?